A fire at a plastics factory in the UK. Mitsubishi develops a plastic recycling plant in Japan. An engineered yeast strain could revive interest in engineered biofeedstocks. And ArcelorMittal plans to use direct reduced iron and smart carbon techniques to reduce the steel carbon footprint.
Hey there, it's Chem Eng Weekly, and this is your month in review.
A fire and some explosions occurred at Leamington's plastic facility plant on the 27th of August. The facility manufactured polyurethane adhesives and coatings with a capacity of 10,000 tonnes per year produced at the plant, and it is speculated that the explosions were caused by the plastic vats and chemical vats that caught fire as the fire spread throughout the building. Residents within a 100-metre radius were evacuated from their houses, and those that lived within 500 metres were advised to keep windows and doors closed, as polyurethane fires actually produce many toxins. They can generate cyanide gas as well as carbon monoxide and some other substances like acetonitrile, acrylonitrile, pyridine, benzonitrile, and carbon soot as other byproducts, which are harmful to people, especially with respiratory diseases. These byproducts are actually heavier than air, so they'll fall to the ground after the smoke subsided, meaning that they could be potentially threatening to anybody who comes into contact with them. One person still remains unaccounted for. The Mitsubishi Chemical Corporation is developing a 20,000 tonne per year hydro-PRS plastic recycling plant in Ibaraki, Japan. Hydro-PRS, or hydrothermic plastic recycling solutions, converts mixed plastics into fossil oil replacements, which can then be used as feedstocks to create new materials such as fabric, plastics, and other items. That means the need for disposal is reduced. It is expected to be completed in 2023 and will primarily aim to recycle post-industrial plastics. Chemical engineers at MIT have engineered some yeast that is genetically tolerant to the toxic conditions given by Biorefinery, which will potentially pave the way for non-viable food feedstocks to be used in the conversion into fuel. Grasses, leaves, stalks, corns on the cob, and other lignocellulosic biomass that is widely available could now be taken into production of fuel. The pre-treatment of the biomass, which is normally toxic to the microorganism in ethanol production, can be overcome by the yeast converting the aldehydes which cause the toxins into alcohol. The engineers used buffers like potassium chloride to strengthen the yeast membranes, giving them resistance and tolerance to the aldehyde and alcohols present, and showed that the yeast within these feedstocks can produce industrially viable ethanol at 100 grams per litre. More development is yet required, but it's hoped this finding will help to revitalise this particular aspect of Biorefinery's industry. Researchers from 4 different universities have developed a single atom catalyst that could be used in the production of propylene, potentially lowering the carbon production through higher selectivity and lower temperature requirements. Propylene is a feedstock used to produce many plastics and chemicals, and at a demand of 100 million tonnes a year, is typically extracted through oil production. However, the movement to shale gas means that propylene cannot be as efficiently extracted, with only a 90% conversion rate of the catalyst used within the propylene production from shale gas. The catalyst only provided 90% of the desired product from the reactions it produced on its surfaces, meaning that it was also prone to coking, and undesired products were also being drawn from this, showing low efficiency and also the need to regenerate the catalyst, which was not time or cost effective within industry. This single atom alloy, which is not random in structure like traditional catalysts, allows 100% selectivity, meaning that 100% of the reactions produce the desired product on the surface of the catalyst. It has also been shown that it resists coking, giving a more efficient process that would have a good economic and environmental turn-up in the long-term future. Finally, ArcelorMittal has pledged that it will use direct reduced iron and smart carbon techniques to reduce its carbon emission intensity by 25% by 2030. The global steel and mining company is set to invest $10 billion in trying to reduce both the Scope 1 and Scope 2 emissions. The direct reduced iron is hoping to use green hydrogen, which will directly reduce any oxygen within the ores found for the hydrogen in their solid state, reducing the carbon emissions within the production processes themselves. And the smart carbon techniques they are trying to employ would be specific to steel renewable energy, such as the use of the Torero production technique, which uses torrefaction of waste wood and plastics. Torrefaction is a thermochemical technique where they attempt to remove any volatiles and water from any fuels like the waste woods, as you mentioned, giving a higher purity fuel and more efficiency in the burning process overall. The company has said it's not quite commercially or economically viable just yet to be driven towards a net zero using this technique. However, they hope to set their goals within 2 years and hope that there will be more clarity within that time. And that's it. Those were the biggest stories of August 2021.
Thank you for watching the video. Be sure to like it if you enjoyed it and leave your comments and suggestions down in the comments section below. Don't forget to follow us on our social media channels, and if you click here or here, you can watch another one of our videos. Click up here to subscribe, and thank you very much.